Okay. So the next part is looking at how temperature affects rate. And for the most part, and I can't think of an instance where you won't see this, increasing the temperature increases the rate. And in order for a reaction to actually occur, it needs to have enough energy called the activation energy. Oops. In order to basically overcome any sort of barrier. And there's an energy barrier. We're going to see lots of diagrams with this, and that barrier is referred to as the activation energy. So one of the ways you can overcome the activation energy, which we are going to abbreviate E sub A, is use heat. Okay, so increase the temperature. If you remember back to gases, when we were talking about the kinetic molecular theory, you increase the temperature of the gas, the molecules move faster, they have greater kinetic energy. That's going to be the same thing here. It's going to allow reactions to occur more quickly. We can relate temperature and rate through what's called the Arrhenius Equation. Okay. The Arrhenius Equation says that our rate constant K is equal to A, which is a frequency factor, we'll talk about that, times E raised to the minus EA over RT. And all of this is in the power, EA over RT. And in this instance, our gas constant is 8.314 joules per mole Kelvin. And because we're using that gas constant with that temperature unit, our temperature needs to be in Kelvin. Really easy way to make a mistake is to forget to use Kelvin and use Celsius instead. Okay, so again, we have our activation energy, okay, amount of energy that's required for a reaction to occur. And then we have our frequency factor. So let's talk about what that is. So we're going to skip this because I've just stuck an extra slide in there for some reason. Okay, so again, here, our Arrhenius equation is written. And we have a plot that shows our rate constant versus temperature. And you'll notice that the rate constant increases as the temperature increases. When the rate constant increases, the rate is faster. Okay? And so what we see happening is as we increase the temperature, we see more collisions. And that increases our K because there's a greater number of collisions with the right amount of energy. And so I really like this figure. So this figure shows the number of molecules with a certain kinetic energy. Okay? The dotted line represents our activation energy. So the molecules need to have energy greater than this, okay, in order for the reaction to proceed. And as we increase the temperature, we increase the distribution of molecules with a greater energy. And so the shading in the plot represents the fraction of molecules with enough energy to overcome the activation energy. As we increase the temperature, we see more molecules that have that amount of energy. Okay? I think this slide works for a number of topics that we've talked about so far, actually, even with solutions. So questions on that? So the frequency factor is related to the number of collisions with the right energy and proper orientation. We'll talk about what that means. Okay. So let's take our Arrhenius equation and let's get it out of this exponent. Let's take the natural log of both sides. Okay, and we'll end up with an equation that is the natural log of the rate constant equals the natural log of the frequency factor minus E sub A over R times 1 over T. Man, that's ugly. ln of k is ln of a minus EA over R times 1 over T. There. That's better. Again, yes. What's that? Oh, I did that on purpose. You could. But I did that on purpose because you know how we like to write things in the form of y equals mx plus b. That's exactly what we have here. Okay, where our x-axis is going to be 1 over the temperature, and our y-axis is going to be the natural log of the rate constant. Okay. And in plotting data of rate constant versus 1 over natural log of rate constant versus 1 over temperature, you should get a straight line plot with the slope equal to minus EA over R. And so from this type of data, you can calculate the activation energy for any reaction. Actually not given this equation, okay? This is a lot of stuff, okay? Let's say this, for the exam, you are given this equation. And so this is the 2-point Arrhenius equation. Basically what we do is we find the difference between 2 points on the line, and we end up with this expression. So this allows us to predict the rate at a temperature if we know the rate at one temperature. So oftentimes we know the rate at temperature 1, and we find the rate constant at a second temperature. Okay. So we're going to do an example. I'm not going to walk you through how this is derived, but again, related to the number of collisions, as we increase the temperature, we should see an increase in our rate constant, and larger EA, larger K. I don't think this is right. I'm going to cross that out. Don't read that one. Okay. Using this 2-point equation. So we could take our two rates, 1 and 2, and our two temperatures, 1 and 2, make sure they're in Kelvin, plug those in, and calculate E sub A. Okay, I'm not going to go through that. Oh, I guess we aren't going to do, oh yes we are. All right, this is sort of hidden in here. So let's take a reaction of nitrogen monoxide with chlorine gas. We're going to form NaCl and chlorine. Okay. So I mentioned that reactions have to occur with a certain amount of energy, with certain orientation. We're going to take a look at that, but I wanted to point out one thing. Where this reaction at 25 degrees Celsius has a rate constant of 4.9 times 10 to the minus 6 liters per mole second. If we increase the temperature during the reaction to 35 degrees Celsius, that rate jumps up almost threefold, or maybe a little more than threefold, to 1.5 times 10 to the minus 5 liters per mole second. So in many cases, the reason this occurs is simply because of collision theory. Yes?
Is it a Cl ion or is it diatomic? Or just Cl?
It's just Cl. It's just Cl. Yeah. So, So I said that the reactants need to collide with a certain amount of energy, and that energy is our activation energy. So given these data, we could actually calculate the activation energy for the reaction. That is a thing you could do. But I want to talk a little bit about this collide with proper orientation, because this is kind of neat. So in order for a reaction to occur, the atoms that are going to form a bond need to be adjacent to each other. So NO is like this. We're going to have our chlorine with single bonds. And the product that they're going to form is oxygen double bonded to nitrogen, single bonded to chlorine, and then the other chlorine. Let's say that the chlorine sort of comes in close next to the oxygen on nitrogen monoxide. Is that reaction going to happen? No. The reaction won't occur if it comes in that way, but it would occur if we had something like this. And I'm going to cheat, and we'll go there. Okay, so the nitrogen on nitrogen monoxide must come in contact with the chlorine. Okay. Now, I'm not going to run the PhET simulation. We're almost out of time, but there is a really cool simulation that I will send you a link to on Slack that kind of walks you through collision theory. So you'll be able to see what happens if the molecules don't collide properly. You can see the effect of increasing the temperature and see the molecules moving faster, and more will have a greater energy. You can also build, on Wednesday, we'll pick up approximately here. Yeah. Show you that, and these reaction progress diagrams. So you'll be able to see the activation energy, so that's E sub A, which is the amount of energy it takes to get over that hill. So I'm going to send that out. You guys can play.